So this is Unit 5.3. This is noble gas configuration and isoelectronic ions. So last class we left off with talking about two things. One, your new model of the atom, so your quantum mechanical model. And remember the quantum mechanical model, it's very different than we learned in grade 9 and grade 10. What has really changed, there's still neutrons, there's still electrons, there's still protons, there's still a nucleus, but what's really changed is the electrons and how we look at them now. So these electrons are not just perfectly going around a nucleus in nice little orbitals or shells. You're doing so in a very diffuse kind of matter, this idea that now electrons kind of orbit the nucleus in what are called electron clouds. And so things are not as defined as they were in grade 9 or grade 10, so it's not as simple. And so we discussed last class a better way to think about this because the orbitals are so different in their shapes. S orbitals are spherical, P orbitals look like two balloons, D and F orbitals are super weird, they're like multiple balloons or rings and stuff. So drawing atoms now is too complex with orbitals. So we're going to focus on is more about their energy and which orbitals are filled and how many electrons are in them. And so you learn about electron configurations. And so if you recall, electron configuration is basically a code or recipe for locating all the electrons. Where are they? What energy levels? What orbitals? And that sort of thing. Now, electron configurations are extremely helpful, but we always want to make sure that there are alternative ways to write the same information. And usually simpler is better. And so I'm going to use an analogy here as I do for most things. So imagine you had a friend, and your friend wanted to know, well, how could I get to the Wendy's that's nearby L.A. Matheson? And you might say, okay, well, I looked this up on Google Maps. You could take a left on 122nd Street, then make a right on 94th Avenue, and then make a left on 121st Street, and then make a right on 93rd A Avenue, then make a right on Scott Road, and then walk for 5 minutes down Scott Road, and you're at Wendy's. Okay, so that's a lot of instructions there. Alternatively, you could say, you know where Domino's is? And they nod their head yes. You go, okay, well, just walk up Scott Road from Domino's for 1 minute, and you're at Wendy's. So a big difference between the two sets of instructions, right? The first set of instructions required a lot more information than the second. Well, why is that? Well, simply put, the second set of instructions used a reference point. Anytime you have a reference point, you basically save yourself a lot of information because you can now use that as your new starting point. Okay, so reference points are basically somewhere that is already further along the path, and therefore you can basically save some time and information by using that reference point. Now, when it comes to electron configurations, you may have done some that had F orbitals, like Einsteinium or uranium or something like that. And they are extremely long, right? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. You go into the 6th and the 7th energy levels, there's a lot in there. And so using reference points for us is a good way to save a lot of time and convey the same amount of information, just like we did with the way to get to Wendy's. Okay, I just said, here's Domino's. You know where Domino's is? Yep. Okay, walk a minute up from there. Same thing here. For electron configurations here, our reference point is always going to be the closest noble gas. Now, this is important. When I say closest noble gas, I mean closest noble gas that your electrons could have the same configuration as. Therefore, it cannot be a noble gas that has a higher number of electrons than you possess. Okay, it must be a noble gas that is close to you, but is going to be less number of electrons, not more. Again, the logic behind that is, if you're using a noble gas that had more electrons than you have, the reference point is beyond where you actually can be or where you're going to be, so it's useless. It must be a noble gas that you could actually achieve. Okay, so if we do that, below, I want you to write the electron configurations for those noble gases, and then when you're done, come back and we'll discuss it. Okay, good luck. Okay, so coming back, you should have noticed a pattern. Well, what is that pattern? That pattern is this. If you look at your noble gases, first of all, it says in there the exception is helium. Okay, so helium ends at a 1s2, right? It's on the first energy level and it's just an s orbital, so it's 1s2. Every other noble gas ends in the same. They all end in a full p6 orbital. For example, neon is 2p6, argon 3p6, krypton 4p6, xenon 5p6, radon 6p6, and this isn't really noble gas. This is a new element that was just created a little while ago, so don't worry about that one. But the others, the actual noble gases, they all end in a full p6. Okay, so this is kind of your this is your marker, this is your clue. And so when you look at any other noble gas, except for helium, which is the exception, they will all end in a p6. Okay, so they all have a full p orbital. So we're going to teach you something today called a noble gas configuration, or sometimes also called an abbreviated electron configuration. It's the exact same thing as you've been doing electron configurations. The only difference is, just like the instructions above, is you're taking a reference point, your noble gas, to kind of cut down on all of the writing that you do. It's going to save you a lot of time, okay? And it's super easy once you see how to do it. So this is how it works. For example, here's the full electron configuration for cesium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s1. And then I say to you, okay, write the noble gas configuration for this. Well, a noble gas configuration simply utilizes, again, the closest noble gas in this electron configuration. So what you do is you hunt, and you hunt for a noble gas. How do you know when you have a noble gas? You're looking for, if it's helium, 1s2. As you go past helium, they all end in p6. So 1s2, 2p6, another noble gas. Keep going. 3p6, another noble gas. 4p6, another noble gas. 5p6, another noble gas. Are there any more noble gases? There are not. Therefore, I'm going to stop right there. All of this information now can be condensed into a single noble gas. Okay, so if you notice, I ended at 5p6. So if I go back to my periodic table here, 1s2, 2s2, 1s2, 3p6, 4p6, 5p6 is right. Oh, hold on a sec. 1s2, 2p6, 3p6, 4p6, 5p6 is right here, okay? So I can condense all of that information that you would normally write for all of these electrons into one single noble gas. It's going to save you a lot of time. In this case, that would just be xenon, because if you notice, cesium is right here, okay? So its closest noble gas is not radon. Even if it was astatine, you would not use radon. Why? Because radon has more electrons than astatine does. It must be a noble gas that is fewer electrons, because you cannot use something that you do not have a number of electrons to actually use as your reference point. You have to have that number of electrons. So we go back to the least closest noble gas. In this case, it would be xenon here. Or again, you can just look at the electron configuration itself. Okay, so going back, as you noticed, I ended, my last noble gas was 5p6. Therefore, all this information can be condensed into one element, and that element is xenon. And so we put square brackets around it, letting us know that our noble gas configuration is using as a reference point xenon. Last step is you now add in any of your, so basically, if you remember anything to do with noble gases in grade 9 or grade 10, remember that noble gases have full valence shells, right? Or basically in our observation now, full energy levels. Therefore, every single energy level from 1 to 5 is completely full. Hence why it's a noble gas configuration. Okay? Remember, going back, noble gases, they're stable. Why? Because they have full valence shells. All of their orbitals are full. Same thing here. All of our orbitals are full, right? You'll notice now in the next energy level, there's an electron left over. Okay? This information is still here. We still have an extra electron that will be carried forward. But this gives us some extra information. So in this case, first of all, our noble gas configuration is going to be xenon, it's a reference point, and then what's left over, a 6s1. Okay, it lets us know we have the equivalent number of electrons as xenon plus one extra electron in the 6th energy level in an s orbital. Okay, so if you compare these two, this electron configuration compared to this one is a lot quicker to write, right? It's a lot easier. But what about the 6s1? What else does this tell us? Well, it gives us one important piece of information. Oh, before I get into that, sorry, I should have said that. You cannot use a noble gas as its own noble gas configuration. So for example, I could not take xenon and say the The noble gas configuration of xenon is xenon. That doesn't give me any information. Okay, so again, just like any element, your noble gas configuration must be the closest noble gas that is less electrons than you have. Therefore, if I were to say, what's xenon's noble gas configuration? You can't use xenon. I'd have to go back. What's the first noble gas I encounter? It would be krypton. I'd use krypton as my reference. So square brackets krypton, and then this is the fifth. 1, 2, 3. This is the fifth. So 5s2, 4d10, 5p6. Okay, so you cannot use a noble gas for its own noble gas configuration. And more importantly, if I were to say, what's helium's? Well, there's nothing below helium, so it would have no noble gas configuration. And of course, hydrogen has none as well because there's nothing below it. Okay, so again, if you're picking a noble gas, it is always the noble gas that is below the number of electrons that you have. Okay, so if I have iodine, am I going to use xenon? No, it has more. I'm going to use, go back, I'm going to use krypton. So be careful with that. Okay. Sorry, I just mentioned out there. Okay, so what was this whole thing I was mentioning here with this extra electron? Well, this goes back to what you did in grade 10, hopefully. So noble gas configurations, in addition to, of course, being good reference points, they also help you determine the number of valence electrons in your element. If you remember, valence electrons are only those electrons in your outermost. So in grade 10, you learn these are the electrons of the outermost orbital. Well, same logic here. The outermost orbital, also the outermost energy level. Therefore, whatever electrons are not part of your noble gas configuration, they are a valence electron. So if you go back to cesium here, cesium is xenon, right? Every electron is placed in an orbital and is filled, and then it's 6s1. This is an electron in the 6 energy level all by its lonesome self. Therefore, it is the one valence electron that cesium has. Okay? So again, these will give you your valence electrons. Okay, a little bit of practice. Below, what I want you to do is take each element, figure out what's its electron configuration, then figure out what its noble gas configuration is, and then determine how many valence electrons are in that element. Okay, good luck, and come back once you're done. Okay, taking a look at our answers here. For the first one, chlorine. Chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. In this case, noble gas configuration, what's our last P6 or S2? It's right here. It's 2p6. 2p6 is neon. So neon is our reference noble gas. So our noble gas configuration is neon, and then we're left with 3s2, 3p5 at the next energy level. Therefore, we have 7 valence electrons in our outermost energy level. Next one. Oh, I guess that was my example one. I should have known that. But anyway, is calcium. For calcium, it is, I probably should have written these out. Sorry about that. I apologize. Well, hopefully you can determine these on your own anyway. But for calcium, so calcium, aluminum, silver, and krypton. Calcium, aluminum, silver, and krypton. So for calcium, closest noble gas is argon, and then it should be 1s2. Therefore, it has 2 valence electrons. For the next one was aluminum. For aluminum, its closest noble gas is neon, so that would be your reference point, and then it's going to be 3s2 and then 3p1, so a total of 3 valence electrons. For neon, neon is right here. Its noble gas configuration is going to use the closest noble gas, which is helium, 1s2. And then it'd be 1s2, and then it'd be 2s2, 2p6. Therefore, it has 8 valence electrons. And finally, silver, which is right here. Silver's closest noble gas is going to be krypton. And then after krypton, it's going to be, so 1, 2, 3, 4, 5, it's going to be 5s2, 4d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 4d9, 9 and 2 is 11 valence electrons. Okay, so that's how you would determine those. Oh, I did aluminum, silver. I did the wrong one. Sorry, krypton is argon. I apologize. Okay, and that is how you do your noble gas configuration. So I'm not going to give you a worksheet for it. What I did was I just said the sheet you did for 5.2 We wrote down all the electron configurations. Just beneath those, write out the noble gas configurations. So there's a total of 20 of them. So write out the noble gas configurations for every single one of those. Okay, and once you're done, at the end of this video, I will show you the answers for those questions. Okay, and finally, the last little part here, it's a small little add-on, is isoelectronic elements. So since ionic forms of elements can have different numbers of electrons, any ions or atoms with the same number of electrons are referred to as being isoelectronic. Iso means basically the same, in essence, the same number of electrons. So again, going back to grade 9 and grade 10, if you recall, ions form, why? So an atom can become stable. What's stable? Having a full outer valence shell or energy level. Therefore, metals tend to lose electrons, becoming positively charged, and of course, nonmetals tend to gain electrons to become negatively charged. So for example, F-1, and so fluorine with a -1 charge, and neon and magnesium with a +2 charge all have 10 electrons. Therefore, they all have the same electron configuration, and therefore they are all isoelectronic. Okay, so again, whether it's an atom or whether it's an ion is irrelevant. What's important is the electrons. Are they different? Are they the same? And therefore, how does this affect the electron configuration? So for example, aluminum +3, magnesium +2, sodium +1, F-1, O-2, N-3, they are all isoelectronic. Every single one of these has exactly 10 electrons. Therefore, they would all have the exact same electron configuration as neon. Are their nuclei the same? No. Different numbers of protons, hence why they're different elements, but their electrons and energy levels are the same. Okay? So, let me get you to try this. I don't know the answers. Which ions have electron configurations isoelectronic to argon? So for example, let's find argon on our periodic table. It is right here. So again, if you don't know the reason, remember, the reason why atoms become ions is to, again, become like the closest noble gas. If you remember, noble gases are stable because they have full outer valence shells. And therefore, these atoms will form these ions to become like the closest noble gas. So for example, if we're talking about argon, in terms of nonmetals, phosphorus -3, sulfur -2, chlorine -1, these ions all have the exact same electron configuration as argon. Why? Because every single one of them has 18 electrons. 15 + 3, 18. 16 + 2, 18. 17 + 1, 18. So they all have 18 electrons, therefore exact same electron configuration as argon. Metals in the other case, potassium +1. Calcium +2, scandium +3. Every single one of these has the exact same electron configuration as argon. Why? 19 - 1, or if you forgot, a +1 charge or a positive charge means that's how many electrons you've lost. So 19 - 1, 18 electrons. 20 - 2, 18 electrons. 21 - 3, 18 electrons. Therefore, they all have the same number as argon. Again, therefore, they would all have the exact same electron configuration. Okay, so these would all be, and there are lots of other examples you could find on there, but that gets you an idea of it. So again, be aware of that. Okay, on your 5.2 sheet at the very end, right underneath your electron configurations, your noble gas configurations. Once you're done, come back and check your answers. Okay, let's take a look at your work. Starting with 1 to 5 here, please take a look. And if I've made a mistake, definitely let me know so I can let the class know. Okay, moving on, 6 to 10. Okay, moving on, 11 to 15. Good thing is you can stop your video for as long as you need to check the work. And finally, 16 to 20. Oops, cut off Einsteinium there. Okay, so hopefully this is going to save you a lot of time in the future. Okay, good luck, and I will see you soon.